Just since we're on the topic of digital and analog, I wanted to just briefly show you some examples of images and sounds and just talk about video a little bit. So just because you can see it. So as I was saying before, JPEG is like the famous lossy format. So of course, we've all seen this image, the famous yellow flowers image. So what happens with JPEG, which stands for Joint Photographic Expert Group, which was a committee that met years ago to just set up a standard for, well, what should be the format for storing a compressed image. And what's funny, because I'm sure that committee was just like a complete dusty backwater at the time, and yet JPEG has turned out to be like the Rosetta Stone, right? Every phone, every computer is just being used constantly. Like they could never have imagined how widespread that work was going to end up being. So I should mention JPEG is a free and open standard. So no permission is required to use it, and it has that quality of standards that if my digital camera formats images as JPEGs in that format, which is it's about bytes, so it formats the bytes as JPEG, then it can be confident that that data can be handed to a web browser or a phone or any other sort of hardware out there, and the designers of that hardware have also read the JPEG standard, and so they know how the bytes should be arranged, and so then my image taken from one place works everywhere. And so this is the classic advantage of standards. So when an image is recorded in JPEG, there is this knob of how compressed should the image be. And I want you to think of this as, I'm going to call it the Q number, the quality number. And I'm just going to imagine it ranges from 1 to 10. So let's say when the Q number is set at 10, the least amount of throwing out data happens. So the quality is going to be the highest, and the amount of space it takes up is going to be the biggest, right? So if I turn it up to Q10, it's like, some aliens have landed. You're taking the picture, and you're like, wow, I really don't want to have any mess ups, so I'll record it with highest data. But it takes the biggest amount of space. So normally on your digital camera, no one uses Q10. The trade-offs are terrible. So a typical setting would be maybe something more like what I'm going to call Q5 or Q6, kind of in the middle of the range, where JPEG throws out a little bit of the data, but it's imperceptible. Like MP3, when I say throw out data, I feel like it kind of makes everyone a little bit nervous, but it is well studied and well designed, so the data it removes, it's imperceptible. So just in standard operation with your digital camera, it's probably recording the images at Q5. Or something like that. That means that if you edit it later and save it at some higher setting, it's pointless. Because it recorded at Q5, so whatever lossy is in there has already happened. That's what was recorded. Sometimes the cameras will have what is called a RAW format for like really picky uses. So the RAW format means no lossy compression. Just record all of the bytes of the image untouched, and and then on my computer I'll edit it and futz with it later. Okay, so this is our original flowers image. We'll call that Q5. So what I did is I saved successive versions of the image, turning the Q knob lower and lower, so you could see how it is that the lossy JPEG quality messes up the image. And the main thing I want you to remember, I want to show you these artifacts, is that JPEG does a really good job. It is very hard to see the things that are introduced. The term for the little visual mess-ups that are introduced is sometimes they're called artifacts. Or sometimes you'll see compression artifacts, where an image, the knob has been turned down so far that you can begin to see where JPEG is throwing out data. So anyway, I guess what I'm saying, so although I'm going to talk about artifacts, I don't want you to walk away here with some uneasy feeling of, where's my data? Like, for the most part, this works great. I just want you to see how it works. All right, so there's Q5. Let's see. Oh, I'm sorry. This is how my camera takes it. I'm sorry. We'll call this Q7. It's actually not documented for my camera, but I think Q7 is a typical figure. All right, so here I resaved. So this one takes 48 kilobytes compressed. So here I saved it as Q5. So I turned the knob down, and now it takes 29 kilobytes. So that was saving about what, 20 or 30%? 20 or 30% less space. And I look between these two, and I just cannot see any difference. Like it saved 20%, but like, I don't know, I can't see it. So I kept turning the knob. I'm going to turn the knob lower. Okay, so here I turn the knob down to Q1, the absolute lowest possible. And now it takes up 14 kilobytes. So that's about 3x or 4x. That is an enormous compression, right? I mean, it's reduced by a factor of 3 or 4 the amount of bytes that this is taking up. So if you just glance at this, I think it still looks OK. But what I'm going to do is I'm going to zoom in. And zoomed in, you can actually really see the effects. And so what I'm going to do here, let me fix the lights a little bit here. All right. So I'm going to zoom in on this thing really as close as my browser can go. So sort of putting it under the microscope so we can see what the artifacts are. OK. So that's the Q5 one. Still looks pretty good. So here's the Q1 one. I don't know if you guys can you guys see the little squares in the image? Maybe I can find a section where they show up better. Oh, there we go. So look over here at this green leaf. So if you look carefully, you can see really the way JPEG works is it groups the blocks of the image into 8 by 8 blocks of pixels, so 64 pixels at a time. And it kind of deals with those as a group and does some of the compression by that group. And so if you look at this image very carefully, you can actually see the sort of checkerboard pattern that's coming about because of the blocks. So that is one JPEG artifact that you might see. Another thing, which you can see here at the edge of the flower, see how there's yellow and then there's white, and then you see how there's this kind of like this fuzz coming off the other side in an area that probably should be just black or dark gray. So that is a classic JPEG artifact. And what's happening is that JPEG has a hard time with boundaries, really sharp boundaries between one color and another. And so here what's happened is the yellow has kind of bled over into this kind of snow, poking a little bit into the other side. Now, in order to see this artifact, I had to turn the knob all the way down to 1 and then zoom in as far as we could. But I definitely do see this. In real life, I see this artifact sometimes. One time probably where I see it the most is actually in video encoding. So like in DVD movies, sometimes if you see there's some video material, but then they've put letters like the titling for like produced by, directed by, or whatever, the letters present exactly this case of a very sharp color with a sharp dividing line and then some murky color behind it. And so the compression for DVDs actually suffers from the same artifact. And so this could be an added dimension to your movie watching. You could stop the movie and go up to the screen and look really carefully, and you might see the same kind of artifact. So another place where this kind of compression is used is in cable video and especially satellite video. So that's the satellite TV where they have like a zillion channels. Well, how is it that they're fitting all those channels onto that one dish? And the way they're fitting it on there is with heavy compression. They're taking the video stream and they're like, well, if we compress it this much, we can fit 100 channels. Ooh, but if we turn the knob down another notch, then we can fit 150 channels. And so the tendency has been, just the way advertising revenue works and just that you can advertise a lot of channels, the tendency has been, in my experience, is that they compress it pretty heavily so that they can have a lot of channels. So it uses up fewer bytes so they can fit the most channels. All right, let me turn the lights back up here a little bit. OK, so I'll zoom back out here. Oops. OK, there we go. OK, so that was the most compressed one. All right, so I've talked about this math before, where you could work out the number of bytes that an image should take up. So that image, it's about 400 by 300. So let's say that's 360,000. I'm sorry, that's 120,000 pixels. Let's say the flowers image. So you just multiply the width by the height. I think I did the math for this before. So each pixel takes 3 bytes, it turns out. So the red number, the green number, and the blue number. each takes 1 byte. So per pixel, that's 3 bytes per pixel, 3 numbers per pixel. So you just multiply. So the number of bytes for one image should be something like, or for that image, should be something like 360,000 bytes. But if you go on your flash drive and you look at an image you have, or you look at this image, this one takes 48 kilobytes. So what is that? About, it's a little less than a factor of 10. So why does it take up so much less bytes? JPEG. All right. Partly by being lossy, but partly just by being smart about how it arranges the data. JPEG causes your images, as naively you would think how many bytes they take up a lot less space. So that's just going on all the time. All right, so I've already sort of talked about this. So I'll just mention other formats, GIF and PNG. Those are, so JPEG is optimized really for digital cameras for images of things in the real world that have kind of texture and parts that are in focus and parts that are out of focus. Just all those qualities of real images. JPEG is geared for that case. The formats GIF and PNG are optimized more for, you would think of like logos. Or I was thinking of like The Simpsons. Something where it's a drawn thing. It's got these perfect areas of colors with these sort of perfect boundaries between them. It's optimized for that case. But in reality, you could use PNG to compress, to store anything. As I mentioned before, PNG is lossless. So whatever image you put in, it comes out exactly the same. PNG just reorganizes it to take up less space, but it preserves the image perfectly. All right, I talked about audio a little bit before. That's always right. AAC is the more slightly better Apple one for that. There is actually this format Ogg Vorbis. So MP3 and AAC are both patented. So in some sense, you need permission and to pay some licensing fee to legally play back that data. Although eventually those patents expire. The format Ogg Vorbis was designed to work around those patents. So it's like JPEG, it's just a free and open standard. So in rare cases you may see, or for certain, if redistributing data and avoiding weird legal problems is an important goal of your project, then Ogg Vorbis might be a good example, a good format to use. It performs better than MP3. It performs quite well. There's sort of a funny, I'll just make a side note, kind of making fun of Ogg Vorbis a little bit, which is, who came up with that name? Right? I mean, if the idea was for this format to be popular, and I think this is a classic nerd error, it's some kind of inside joke of referring to a character from some video that no one's ever heard of, and I think there's some Latin subtext to it or something. So anyway, this is an example of like, well, you want to think a little bit about marketing. If you want to create something that people are actually going to use, don't get all wrapped up in your echo chamber with your little cute inside jokes. Like maybe create a name that people would actually like. So I think that was a tragedy. Like they chose this, in my opinion, awful name 10 years ago, and I think, yeah, it's caused a series of legal and media problems for God knows who since then. All right, so let's just talk briefly about video formats. So video data takes even more space than audio. It takes the most. In fact, video data, you can think of it, the way it's made is it's a series of images, so maybe something between 30 and 60 images per second, and also audio data, which then is it's sort of synced up and played at the same time, and obviously that's a movie. So video data, right? It's however big those JPEGs are, let's say 30 times per second. So you can imagine that ends up taking up a lot of space. The good news is that in the same way that I was describing redundancy in an image where a pixel and maybe a pixel just to its right, the numbers are maybe pretty similar, so there's a room to take advantage of that and compress it. Video data, suppose I'm videoing this class, I'm looking at you guys, and I have one grab, so there's an image, and then a 30th of a second, I have the next image. They actually probably look really similar, right? All these seats that are green and the wall, whatever, all those pixels mostly haven't changed, or if a ball was thrown, it was kind of moving across the scene. There'd be some change, but a lot of the pixels from one scene to the next would either be unchanged or would have moved a little bit. And so I'll just say that is an additional source of redundancy. That if instead of encoding a frame just naively the obvious way, you encoded it and you try and think of it as, well, how is it different from the one that came just a fraction of a second before? And you just encoded that difference. There's a lot of redundancy to take advantage, even without being lossy, there's just a lot of redundancy to take advantage of there, so it is possible to make video, to store it in a way that takes up a lot less space. So all the video formats take advantage of that. And so if you just worked it up naively, just in terms of pixels, what would be a colossal amount of data, it's still a lot of data, but it gets down to kind of a reasonable amount. So just kind of as a working number, you could think of video as taking about 2 gigabytes per hour. And the one thing you'll notice is that if you have video data and it's in one format and you want to encode it or reduce it or whatever into some other format, has anyone ever done this on their computer? What you'll find is on the computer, it takes it a long time to take like 1 hour of video data and translate it. It might take on my computer maybe 4 hours. And the reason is just that the computations to try and look at each frame and then think about how the next frame is mostly similar but a little bit different, it's just complicated. And so if you think about having a fast computer nowadays, I think of it as mostly pretty pointless because like whatever, I'm just running Firefox all the time and like it's fast enough. And then mostly my experience is based on how fast the network is. And then the CPU on my machine, it's not really doing a lot. Video compression would be the counterexample. Video compression uses everything your CPU has and more, and it's still pretty slow. So now that's of 2012. So I'm sure if I were to locate this lecture in 2020 and Moore's law has clicked over 2 or 3 times, then that won't be true anymore. We'll be like, oh, video, what are you talking about? It takes 2 seconds. But anyway, as of now, that's one thing that actually takes a short amount of time. So there's a few different formats. There's this thing called the Motion Picture Experts Group that standardizes video formats that are used on DVDs and now on Blu-ray discs and actually on the internet, on formats that are used for like YouTube and Flash video, those sort of things. So there's standards for that. Unlike JPEG, these are very heavily patented. You can't use them for free. They're fairly complicated. And there's some somewhat onerous terms having to do with that. Google, to its credit, wanted to create a format that would be sort of the analog of Ogg Vorbis. Ogg Vorbis is to audio, a format for video encoding that was patent-free. So, for example, if you're Wikipedia and you want to distribute all these videos and you don't want to be in some legal mess of like, well, do my users have permission to watch this legally? You'd like just what is called an unencumbered format. And so that's what the WebM project is. It performs similarly to the top commercial codecs, but it is said to be patent encumbered. But now there's been a legal tussle about this because the patent holders, of course, they want to say like, of course my patents are represented in your technology, because that's what patent holders always say. But ultimately it has to kind of get resolved in the courts or some kind of payment or something. So that controversy continues. But it is I appreciate that they're trying to make an unencumbered format, just so it is possible to distribute video without these patent problems. There was something else I was going to say. Oh, right. So I should mention currently the top top video format is called, it has a terrible name, H.264. Is a very widely used video compression format. And I probably use the word codec there. That's a word that means kind of the encoder. So H.264 is extremely popular. It also works very well. It's very aggressive and very clever in its way that it's able to reduce a video stream down to a fairly small file. So if you ever take a video with your phone, remember those little flip video cameras? Anyone have one of those? So those all take the video stream and in real time compress it down to H.264. So that's a very common, although heavily patented format for that kind of thing. All right. So the last thing I'll mention is that so up till now, the most common way to watch video, probably on the internet, is YouTube. Right? You guys have heard of it? Okay, kittens. You guys seen kittens on the internet? All right. So YouTube, there's a certain amount of technologies there so that it can take video and make it work kind of in a web page. And historically, YouTube has used this technology called Flash. Flash is actually not a standard. It's a product. It's a product that comes out of Adobe. And so almost everything that works on the internet, HTML, JPEG, PNG, HTML, everything, there are all these free and open standards. So Flash is this one kind of oddity in that it's a product. And so your computer is in some sense dependent on Adobe to produce the Flash player. And this is something that famously drove Steve Jobs crazy. Because it meant that if Adobe had some bugs or a slightly lackluster job of producing the Flash player on the Mac, in some sense it made the Mac look bad. Whereas for JPEG, Apple could produce the software on the Mac that rendered JPEGs. And so if Steve Jobs was saying, hey, I want it to look perfect, he could yell at the engineers to make it look perfect, and indeed it does. Whereas with Adobe, because it's not a standard, they had this slightly oddball situation. Anyway, Adobe's Flash has been very successful, but it does have this oddity for how it works on computers where it doesn't really fit with the entire rest of the way the internet works. So enter HTML5. I maybe talked about HTML5 before as adding some features to how web pages work. So one of the features that's being added is what's called the video tag. And the way the video tag works, just to summarize, is it standardizes how video works in a web page so that you could put a video in a web page just as up to now we've put images. Right? Images in web page, we've been doing that for years. You just put it in the image and it just kind of works. The video tag is going to try and recreate that for video. And that's just now coming into use. But I think that's a good thing. It will, in the same way that images work very easily and reliably on the internet, it would be nice if video was open in that way as well. Blah, 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 blah. OK. All right, that is enough for today. Welcome to Knowledge about Analog and Digital. And I'll see you guys on Thursday.